Hello everyone. We will next what we will deal with is the classical BSM, but with a change in the dividend paying stocks. Okay. So, recall that so far whatever we have done, we have assumed a non dividend paying stock as the risky asset, right. So, so with this only, like whether it is binomial model or the BSM model with one stock or BSM model with M stocks, right. Whatever we have assumed so far is that those stocks do not pay a dividend, okay. But it is generally the reality case is that the stocks do pay dividends, okay, and hence it will be worthwhile to consider the risky asset as paying a dividend and how that affects our risk neutral pricing formulas. Okay. We will be in a simple and setup of exactly classical BSM with only change as dividend paying case is what we will consider, but whatever we are doing, it can also be considered in more general with M stocks and D Brownian motion case, which is what we call it as the multi-dimensional BSM market model. Okay. So, now consider dividend paying stock. Okay. So, this is what we will now consider. Okay. Okay. So, that is the change, and let us we will consider here the two cases, but before that just recall that the what we had or how we arrived at the risk neutral pricing formula. What we did was we first showed that the discounted asset prices, which is discounted stock prices, are martingales under a risk neutral measure which we have constructed using Girsanov theorem, and that implied that the a self financing portfolio value processes that you are considering, which the portfolio consisting of asset, this risky asset and the risk free assets of the underlying model, is also the discounted version of that is also a martingale under the same risk neutral measure, and that led us to the risk neutral pricing formula. So, what we needed was this self financing portfolio process, the discounted version of it be a P tilde martingale is all that we needed in order to pin down the risk neutral pricing formula, right. But that was aided by the fact that the discounted asset prices are P tilde martingale, right. So, that was the case when we considered a non dividend paying stocks. Now, in the dividend paying stocks, right, if we have to have the same scenario, of course, obviously since the dividends, and as you understand, the dividends reduces the stock prices, right, whenever it is being paid, and that stock prices, if you look at only the stock price process alone, that may not be a P tilde martingale, right. So, what we take is that suppose if that gets reinvested, because this is going to be a self financing portfolio process, which means no money you are taking out in between, having said that this is the initial price. So, after that once the process started, then you are not taking out any money nor you are putting in any money. So, the self financing portfolio process, if you look at it, then with dividend reinvested in the stock, right, the underlying stock prices process will be a P tilde martingale, and that makes the discounted portfolio value process a martingale. So, that is the point that we pick, right. A risk neutral measure which we define as if it makes the discounted value process, portfolio value process a martingale. That is the measure that we will take, and this is exactly similar to what we have done in the case. Okay. Now, so what is the major change that you might observe is that stock price process need not be a martingale under P tilde, whatever we define, but the stock price process with the dividend reinvested in the same stock will be a P tilde martingale. We pick that a P tilde, and that P tilde would be, I mean, if you make an analogy, it is as if the dividend has not been paid out, right. So, that is what will turn out to be. Okay. Now, while talking about dividends, there are two cases really here, right. One, the dividend is paying at continuously at some rate, the other discrete dividends. Okay. Now, in general you would find most of these formulas assume that the dividend rate, a continuously paying dividend rate is what would be assumed. Okay. The reason is that for a well diversified portfolio, for example, if it has so many assets in its as its component, and each asset might pay dividend at various random times. So, this is itself as if the whole portfolio is paying dividend at a continuous rate. So, this will be more appropriate, or this will be more approximate to such a situation. But as far as single asset is concerned, right, it may be prudent to view as if the dividends are being paid at some discrete time points during your time of consideration, which is typically 0 to t, right. So, you may expect, for example, if you take a typical stock, you may expect that 3 to 4 times in a year, depending upon the financial situation, the a stock may pay a dividend. So, it may be assumed that discrete dividend. So, let us deal with both cases. First, what we will do is that case 1, which is basically continuously paying dividend, is what we will consider as the first case. So, our model, everything is the classical BSM setup, except that the stock price process. Okay. So, what we have now is that, so stock is being modeled as a geometric Brownian motion, right, and the rate, which is what we call it as the dividend rate, is we pick it to be some quantity A. This is A per unit of time. Okay. So, what you have? So, A is typically in the interval 0 to 1. If A is equal to 0, if you put, which means this corresponds to the case where there is no dividend is being paid out. Okay. And if A is equal to 1, the whole stock price is being paid out as dividend, and there is no more, the stock exists in the market that you guess. Typically, the rate is belongs to the open interval 0 1, which means there is some positive rate at which dividend is being paid, right. So, that is what is the general assumption that you will have. Now, whenever the dividend is being paid at any point of time, it reduces the stock price by that amount, right. So, the dynamics, so then the stock price dynamics would be dSt is some alpha St dt plus sigma St dWt as usual, if this dividend, this is the rate of return of the stock, minus if the dividend is being paid at a rate continuously at the rate A per unit of time, then A is the rate per stock, right. So, this AST dt would be the amount that is getting reduced by this. So, you look at here the small in a small interval just after t, right, the change in the underlying stock price process would be the stock would grow at the rate of alpha, but it will also reduce by the dividend rate A, and volatility as usual is the sigma parameter that you have it here. So, these basically, and also you also have this risk free rate, okay, as usual. So, this is the description, stock price dynamics, and this is risk free assets dynamics, or the bond or money market, whatever you want to call, is dynamics is as usual. So, this is what is the two dynamics. Every assumptions remains the same as in the classical BSM framework. Okay. Now, if you, as if you know, because this is reduced by the rate A, if you reinvest this dividends in the same stock, then basically you will be adding an additional this A rate to, I mean, you will keep buying more of that ST by that rate A, so that the mean net return, but the mean rate of return of the stock where the dividends are getting reinvested in the same stock would then be equal to alpha as in the previous case. Okay. So, now let us look at the portfolio value. Portfolio, which is basically a self-financing value process. Okay. So, what we have here is that you know, there is some x naught and there is a portfolio position given by delta t, which you hold at each time t, and its dynamics is what then. So, you are starting with an x naught and this portfolio position process delta t. So, your dynamics of this x t would be delta t dst plus, now since you are reinvesting, so this is the amount that you got, AST dt is the amount that you got as dividend, and since you hold delta t number of such stocks, so this is the total amount that you got and that you are reinvesting plus R xt minus delta t st dt, right. So, if I look at my a self financing portfolio values dynamics, right, this will be given by this, right. I can't take out the dividend out of this portfolio value process, then the whole theory will fail, because it has to be a no-beta situation that starting with some initial naught and some delta t process given, then you are looking at a self-financing value process, so that that equals the value of derivative at maturity. That is what you look for, and see if since that is the requirement, right. So, I can't take out the dividend, I have to reinvest the dividend and then look at the portfolio which does that and its value for replication, right, for making it equal into this. Okay. So, now this you can rewrite now R x t dt plus alpha minus R delta t st dt plus sigma delta t, which can also be written as is the usual. Now, so this can be also be written as in the third line here where theta is alpha minus r by sigma, which is the usual market price of risk. Okay. Now, we can define W tilde t to be W t plus theta t, right, and through Girsanov, right, define P tilde under which this is Brownian motion. Okay. So, that implies that this could be written as R x t dt plus delta t s t sigma d w tilde t. So, what we do? It is exactly the same the market price of risk that we take as theta here as well, right. But here alpha is the rate of return of the stock with dividends reinvested. If you are really using the data to calibrate the model, then that is what you, with dividend reinvested, what is the rate of return it is giving, that is what is your alpha is. Okay. So, the rate of dividend is A. Right. So, that is what we need to get, and once we get that alpha, then alpha minus r by sigma is my theta. That theta I will plug it in the z that we zt that and z that we define in Girsanov theorem to get to P tilde, and under P tilde this particular quantity which is within the square bracket here will be a Brownian motion, and hence you write this. And now with this what you can see. Okay. So, this implies now e to the power minus r t x t if I look at, right. So, this will be delta t e to the power minus s t sigma d w tilde t. So, this implies e to the power minus r t x t is P tilde martingale is what you see immediately, right. Once you see this is a e to the power minus r t is a P tilde martingale, which you see immediately with this expression here, which we written in the last line of, right. The discounted wealth process is a P tilde martingale. Then once we have this, so then now if we wish, now if we want to hedge a short position in Vt and Ft measurable and a variable, that is a derivative, right. There is a derivative. Now, we can do the same process as earlier, right. What we did, that we will need to choose an initial wealth x naught and a portfolio process delta t, which gives us a portfolio value process x t such that x at capital T will be equal to V t. The fact that the discounted value of such a portfolio value process is a martingale gives us, as earlier, to land in the same, right, risk neutral pricing formula, right. So, such that it is x t equal to V t, and that means that your usual step of martingale property will give us the risk neutral pricing formula, which is V t is equal to E tilde of e to the power minus r t minus t V t given f t, right, for 0 less than or equal to t less than or equal to capital T. So, it is the process is similar. Once you said that the discounted wealth process is a martingale, once you show under some p tilde, because as we saw that is what gives us the risk neutral pricing formula. Once we have this step, once we have this step, the red underlined step, then from then onwards everything is the same as earlier. For any derivative, if you want to price, then you will use the same idea to get to the risk neutral pricing formula, which is given by this, right. Now, as a note, so you can see the difference between the dividend and no dividend cases is in the evolution of the stock price process. Really did not make any change in the risk neutral pricing, but the stock price process ST will have a different formula now. That is what it is essentially. So, what we saw DST is essentially your alpha, okay, if I want to write under risk neutral, so this is R minus A ST dt plus sigma ST dW tilde T. So, that implies that my ST is S naught e to the power sigma times Wt plus R minus A minus half sigma square times T is what you would get. So, this is what it is, and you know that this is not a martingale in this particular case because of this extra minus here term. So, if you discount even by that or you multiply or take out that term, okay, then you could see, that is you could see that this process e to the power a t and the usual discounted price process. So, this is a p tilde martingale. Okay. So, the discounted value with growth with stocks reinvested would be a p tilde martingale. This is what you would see here. Okay. So, let us with this thing, then we will look at our typical the risk neutral pricing formula for the special case of European call option, what happens. Okay. Right. So, what we have ST is given by as given here, oh sorry, this is T sigma W tilde. Okay. So, this actually, so this is what we have here. This is the note part, that is you can observe that this is what is p tilde martingale. Now, we have, so now like consider this example, my Vt to be St minus k, the positive part is what I am picking up. Now, let us see what changes it makes to the original risk neutral pricing formula that we derived in this particular case. So, let us look at this. We are given, we know that my St is St e to the power sigma W tilde t minus W tilde t plus R minus A minus half sigma square times t minus t. So, look at this is the solution, or this is what is the stock price process is given at time capital T, given that it is at St at time t. So, this is what is the expression where what you see is an additional term of A, R was replaced by R minus A in some sense. Okay. Now, what we want? We want Vt, which is e tilde of e to the power minus R t minus t St minus k, the positive part, this f t. Okay. So, by our usual proper Markov property of this ST, this will be some function of T and ST, right. So, what we compute is that we first compute the quantity CTX, right, which we know how to do that. Now, ST is as given in the previous line, and we need to compute this conditional expectation. Then you can use the same process what we have followed earlier, right. So, let us rewrite some of these crucial steps that we would have done in the earlier case. Okay. Now, for our simplicity, take tau to be as usual t minus t, right. Now, if I apply by independence lemma, okay, by independence lemma I apply. I am not looking at the right side, but I am looking at this conditional expectation where ST is given by this, where ST is FT measurable and W tilde T minus W tilde small t is independent of FT, and hence I can apply the independence lemma to this conditional expectation expression. Now, if I apply, then the function CTX would be given by e to the power minus R tau x e to the power minus sigma under root tau times some y plus r minus a minus half sigma square times tau, right, minus k, the positive part, right. So, this is what would be my this CTX function, where y is minus W tilde t minus W tilde t by under root t minus t, okay, which is normal 0 1 follows a normal standard normal, which is a standard normal random variable under the probability measure p tilde, under the probability measure p tilde. So, we also define as usual earlier the d plus or minus tau x to be 1 over sigma of 2 pi log of x by k plus r minus a plus or minus half sigma square tau, right. D plus involves the plus here, D minus involves minus here, that is what is the expression. Okay. Now, by the same argument that this is the quantity here inside this bracket, we have this positive part of it, this is this quantity, okay. So, this quantity inside the expectation is positive, just like in the earlier case that we have observed, if and only if my y is less than d minus tau x, okay, if I right. So, that means then I can write my CTX to be in this particular form 1 over under root 2 pi. No, you just go through the similar step as to what we have done in the earlier case, okay, except that there is a small minor change in the expression for x, minus sigma under root tau y plus r minus a minus half sigma square times. This particular quantity you can again rewrite right. So, if you just carry out the similar steps, what you would find is the first expression you can write it as this, and the second expression will give you this expression, and if you make the change of variable y plus sigma tau as some z and then simplify this, so what you will end up with this e to the power minus a tau, because this whole expression, if you take out this minus a e to the power minus a times tau out, then it is exactly same as the previous expression, previous time when we did with the case. Minus k e to the power minus r tau n of d minus of tau x. Okay. So, this is what is the expression that you would get. So, and hence my Vt is C of t and St, where this x will get replaced by this. So, what is the change that you notice here? You notice the change in two places. One is in the definition of T d plus and minus. So, you have an extra term here which is minus a, okay, and you also have an extra term here in the form, right. So, this is the effect of this. So, but you have to rederive, otherwise you can't simply replace r by r minus a, because that is not true in general, because in the second term in the expression that r will remain as same. So, it is not that way, you have to rederive, and but derivation has this effect that this is what it is. So, this is the formula that you would find normally is applicable when there is a dividend rate is being applied, which means the continuously paying dividend rate is the case that you are considering. Then you will have this idea, and this is the pricing formula for the European call option when the underlying stock pays continuously paying a dividend, pays dividend at a continuous rate of a, then the time t arbitrage price is given by this BSM formula. So, this is the BSM formula in this case, right. So, this is the case of continuously paying dividend that we have. So, what is the change that it has made? We have seen it here. Okay. Now, look at the case 2 where discrete dividends are being paid, or what one would call as lump sum or lump payments of dividends. Okay. So, what you have? You have see 0 to t as the time interval. There are times, say t0 equal to 0, less than t1, less than t2 and so on, less than tn, which is less than tn plus 1 equal to t. So, these are the dividend paying dates or times, dividend paying times, and dividend is paid at the rate, say here A1, here A2 and here AN. So, assume that in your interval of 0 to t that you are considering, there are some n time points at which dividends are being paid, and the dividend rate at that point of time of payment, or the the proportion is this A1s, and my AJs are as usual. Now, this is not the rate, this is the lump payment of dividend case. So, in this particular case, this is the proportion, right, is what then you have denoting it as A1 A2 dividend paying, dividend dividend paying times T1 T2 Tn, and these are the dividend proportions that you are paying at this point of time, right. Now, between the dividend payment. Okay. So, what happens at time, so at each time, okay, at each time Tj, what happens, the amount of dividend is essentially AJS, we will say Tj minus, okay, where Tj minus means the stock price just prior to Tj. So, the amount of dividend is this, and hence S at Tj would be equal to S at Tj minus Aj times S at Tj minus, which means 1 minus Aj S at Tj minus, right. And between dividend payment dates, what you have, my DST evolves as this for Tj less than or equal to T less than Tj plus 1 for j 0 to n. So, between dividend payment dates, the evolution of stock price process is the usual GBM, geometric Brownian motion dynamics. At Tj, what happens when the dividend is paid, amount of dividend is, we denote it as Aj times Stj minus. So, you determine a proportion, right, between 0 and 1 and multiply by the stock, that is the amount of dividends. The stock price is reduced by the amount of dividend at time Tj. Okay. So, now this completely describes the dynamics of the stock price process at all times between 0 and T. What you have? You start at 0, 0 is not a dividend paying time. So, from 0 up to, but not including T1, the dynamics is given by the GBM dynamics, but at T1 then the stock price process is given by this X dividend price, which is STJs at Tjs at each Tj. So, which is all j from 1 to n. Okay. So, this is j from 1 to n is what then you are going to get here, right. And from T1, starting from T1 until but not including T2, the dynamics is again a GBM with this dynamics, and at T2 the stock price is reduced by 1 minus A2 times ST2 minus is what the stock price. Then from that point onwards again it goes. So, this is the way the dynamics goes in the case of lump payment of dividends or the discrete dividend case that you have. As usual, you have the risk free assets dynamics is as given before, right. So, now in this particular case, let us look at what happens or how do we write the stock price process. Okay. So, what we have, DST is this. Okay. Now, what we do the usual between different promotion. So, suppose you start with a portfolio value process. Suppose if you are looking at it corresponding to some delta t starting with some x naught, then this would be delta t dst, okay, plus r xt minus delta t st dt at all times, right. So, So, this is essentially the between the portfolio process, this is between dividend paying dates, okay, the between dividend paying dates, this is what it is. So, this is again you can see that by substituting all those, because there is no change with respect to the classical case that we have looked at it. Delta t sigma st theta tt plus twt, right. So, again the market price of risk is alpha minus r by sigma. Okay. This is the portfolio value process between dividend payment dates. Okay. Now, at the dividend paying dates, what happens? Okay. The stock price is reduced by, right, the value of the portfolio stock holdings drops by the stock holdings drop by which amount? Aj times delta Tj times S Tj minus, but the portfolio collects the dividends, because this amount is getting reinvested. Okay. But the self financing portfolio collects the dividend. How much? Exactly the same amount, because nothing that S Tj minus. So, this implies that the portfolio value does not jump at this point, at the stock dividend point, right. So, that means, so that implies, so what this means? This means that this is correct for all times t, whether it is dividend paying times or non dividend paying times. So, this formula then is correct for all times t, because self financing portfolio, the stock holdings drop by a proportion, a certain amount, but the portfolio collects the dividend. So, the portfolio value does not change, exactly the same principle as in the other case that we have used, right. So, which means the usual risk neutral pricing formula holds. Okay. Only thing is, now we need to look at how the stock price behaves at various time points. How do we give the stock price in terms of, by incorporating alpha, r, sigma and these Aj's for j is equal to 1 to n. Okay. So, what we have? So, we have the example case that we look at it. Okay. So, now we will take the European call, the same one we will take. We know dst is r st dt plus sigma st dw tilde t. Wait a minute, what did I make? For Tj less than or equal to t less than Tj plus 1 for j is equal to 1 to n, and this implies if I write S Tj plus 1 just before that time point in terms of Tj, then I would get this as sigma W tilde Tj plus 1 minus W tilde Tj plus R minus half sigma square times Tj plus 1 minus Tj. Okay. This is what we get at just prior to Tj plus 1. Now, at Tj plus 1, yes, Tj plus 1 is 1 minus Aj plus 1 times Stj plus 1 minus, right, Stj plus 1 minus, which is equal to 1 minus Aj plus 1 Stj, right. I can write this complete expression here, Tj plus 1 minus W tilde Tj plus sigma square Tj plus 1 minus Tj. So, what we have written here now is starting from Tj up to Tj, but not including Tj plus 1, the dynamics is the GBM dynamics, and hence my S Tj plus 1 minus just prior to that is essentially given by this, right, because the stock price makes a jump at that point of time, and after the jump the value is given by S Tj plus 1, which is given by this expression, which is what we have it here, okay. Or you can write in general, right, or S Tj plus 1 by S Tj is essentially 1 minus Aj plus 1 e to the power sigma W tilde Tj plus 1 minus W tilde Tj plus R minus half sigma square Tj plus 1 minus Tj, and this is true for all of this 0 to n, because S T0 is 0 and S Tn plus 1 is capital T, so that is what you have. So, then this implies my S at capital T by S at 0, if I am looking at it, which is essentially S at Tn plus 1 by S at T0, right, which is nothing but my product of 0 to n S at Tj plus 1 by S at Tj, right. This is nothing but my product of 0 to n 1 minus Aj plus 1 e to the power sigma W tilde T plus R minus half sigma squared times T is what you would get, okay. So, in other words, or my St is S naught times product j is equal to 0 to n 1 minus Aj plus 1 times e to the power sigma W tilde T plus R minus half sigma square times T, okay. So, what we are seeing here as the expression for St in this particular case. So, what we have done between two dividend dates, it is GBM, but at dividend dates the stock price makes a jump, right, it drops by a certain amount, a jump it makes, means jump need not be up, it is jump down, it makes a jump, and by incorporating those jumps, now we are given a final expression for S at capital T starting from 0 up to capital T, how this stock price process can be represented in terms of all the parameters of the model, right. So, that is what we have seen. So, what we are seeing here is this is similar to the no dividend case, with the change that my S naught here, okay. So, in the classical case, S naught in the no dividend case is actually replaced by S naught product of 1 minus A j plus 1 where j is from 0 to n, right. This is what you observe, right, otherwise everything remain the same. Okay. So, this is what you are observing, as if you start with an S naught which is reduced by this quantity, this product of 1 minus A j plus 1, because 1 minus A j plus 1 is something which is less than or equal to 1, typically less than 1. Now, you are making a product of all such quantities. So, as if instead of starting with S naught, if you start with S naught multiplied by this quantity which is less than 1, typically less than 1 or less than or equal to 1 to be precise, then this is what the stock price evolution is given by in this particular case. So, therefore, suppose if I adopt this, so therefore, the price at time 0, now for conveniently we take 0 for the time being, right. So, it is as if you are replacing S naught by this quantity. So, therefore, the price at time 0 of an European call on this dividend paying asset, okay, with K and T as the usual parameters. K is the strike, T is the maturity, right, is obtained as, okay, as the original S naught, in that is replaced by this new S naught, because if you, what it says is the evolution is that as if you are S naught, you are reduced by that quantity, then the complete evolution takes place. So, that is what is we are coming out. So, this means that V at 0 in that particular case will be replaced by S naught product of j is equal to 0 to, oh sorry, there is some change, okay, there is some typo here essentially, 0 to 1 S T j plus 1 and 0 to n if I take, this will be, when I write this, there is nothing like A n plus 1. So, it is A n. So, the last term is actually capital T, T n plus 1. So, I should get this product as A n minus 1. So, and hence this will also be A n minus 1. There is a typo or correction that you may need to look at. Okay. So, this I think that just note the correction that I have just made, that see A up to T n is the dividend paying times, right. There is no T n plus 1 is not a dividend paying time, which is equal to the capital T. So, and hence this product j is equal to 1 to n running is essentially, if I write in this form, then it is 0 to n minus 1. That is what you need to note. Okay. So, come back. So, this is what you will have 1 minus A j plus 1. This is the new S naught times n of d plus, okay, d plus minus e to the power minus r t k times of this is n of d minus where my d plus minus essentially this is would be equal to, so if I want to write with anyway, so this is T and S naught essentially, right, is 1 over sigma under root not tau man T, because time 0 is what you are looking at it, okay, log of S naught by K, the usual term, but plus now the new old S naught is replaced by the new S naught. So, the log of S naught into product of this, so that becomes sum of log of the sum, and again the product becomes the sum. So, ultimately you will get log of 1 minus A j plus 1 plus r plus r minus half sigma square times capital T, right. So, this is the time 0 price. Okay. A similar formula holds for Vt, means the call price at T, where one includes only the terms 1 minus Aj plus 1 corresponding to the dividend dates between T and capital T, right. So, here time 0 we have written for simplicity, which includes all the terms A1 to An. Now, suppose if you are writing this formula, right. So, you can use exactly the same thing instead of capital T. Now, I can write in this particular step instead of capital T, I can pick any T. Then I will look at only those products which are up to that point of time, or after that whatever it is happening, right. So, up to that point of time whatever the dividends are there, which will not come into the picture. So, this whole formula in the sum and in the product that we have written here, it will include only those terms of this 1 minus Aj plus 1 which fall, which corresponds to the dividend paying dates, which fall between small t and capital T, because it is 0 to capital T in this written down case, which includes all dates. Suppose if it is falls after T1, for example, if you are looking at some time between T1 and T2, then the first term will not be part of this product and this sum. That is a change that you would find. Okay. So, no matter whatever it is, now we could arrive at the risk neutral pricing formula or the Black-Scholes formula in this particular case, right. So, this is the BSM formula in this case with discrete dividend case or lump sum dividend case is what then you have here. Okay. So, this is the modification or the change that you will make when you want to incorporate dividends into your analysis, into your model for a dividend paying stock. What is the change that will happen, that is it. Okay. So, with this of course, then we may conclude our discussion on this preliminary ideas of the mathematical finance course, and as a summary of risk neutral theory, what you see is that there are 3 cases: case 1, case 2, case 3 if you want to look at. So, this comes from where? From fundamental theorem of surpricing. That is what is the major importance of this. Okay. So, no in the model, right. So, no risk neutral measure in the or for the model, for the market model that you are considering. So, model should not be used. Case 2, you have multiple P tildes. Okay. So, that makes multiple prices for the risk neutral measure. So, you cannot perfectly hedge, okay, cannot hedge completely or perfectly in the underlying asset. Hence, cannot hedge completely or perfectly in this particular case, but this is reality. Okay. For example, we have not explored, but of course, if you have idea, you will know that the credit derivatives, what one talks about, where the you are bringing inside the model that the underlying asset may or the defaultness, means that the defaultness when you bring inside, then what will happen. So, this is in that particular case, for example, you will have multiple P tildes, but then because you cannot hedge completely with the underlying asset itself, because that itself is a defaultable asset. Okay. So, such cases will happen. So, this is what is multiple P, and the ideal or the very ideal case, so to say, is the unique P tilde, where, right. So, there is a unique price and complete, the model is complete. Okay. So, this is what we have with respect to, for example, the models that we have considered, binomial model and the classical BSM model with one non-dividend paying asset or dividend paying asset, but that is tradable. Important part, that is tradable asset, so that you can take positions in the underlying asset. Suppose if that asset becomes a non-tradable asset, which does happen in reality, in the underlying need not be a tradable asset, then the model becomes incomplete. But dynamics, but when we say classical BSM, we assume the tradable asset, right. So, all those models are complete models, binomial, classical BSM, that is all. Multidimensional model, of course, if you have a unique solution to those theta market price of risk equations, then you will have a unique P tilde. Okay. So, all this no risk neutral measure exists, or the multiple P tilde or unique P tilde, essentially we mean the market price of risk equations, whether it has a no solution case or multiple solution case or unique solution case, right. You go back to that system of equations. And completeness, again, as you understood, based upon the hedging equations, whether it has a solution, okay, which is what the second fundamental theorem guarantees, that if it has a unique solution to the market price of risk equation, then there is at least one solution to the hedging equations, and hence the market is complete. So, that is the ideal case, which is case 3. Case 2 is what normally you would see in most real life situations. Case 1, the model should not be used, and hence you have to change the model, because this model is bad for any usage. Okay. So, in these cases the model could be used, but then the calibration and other issues will come, case 2 case, but that is anyway more, when if you want to explore further, you can look at all those issues that you have it here. So, this is a summary of risk neutral pricing theory for you would have. So, with this we end our discussion on this Black-Scholes model, which is the continuous time risk neutral pricing theory case. Hope that you have understood at least the very basic preliminary ideas behind the mathematical finance, which we have been explored throughout this course. Thank you.